Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to cover one of the most fundamental reactions that you'll need to learn for organic chemistry, and that is electrophilic aromatic substitution. In particular, I'm going to be focused on simplifying the mechanism for you, and of course I will be covering the EAS mechanisms for benzene, nitration, sulfonation, halogenation, and the two Friedel-Crafts, alkylation and acylation. I have a couple suggestions before you watch this video, so if you haven't watched these two already, watch the video recognizing nucleophiles, bases, electrophiles, and acids, as well as watch the video The Organic Chemistry Reactions Problem-Solving Process. By the time you start learning about EAS reactions, you've already learned about aromatic compounds and the fact that they are particularly stable. So if they're so stable, what makes them reactive in the first place? If we go back to our general definition of what a nucleophile is, it's a region of excess electron density. And benzene, as well as other aromatic compounds, are nucleophiles because they have excess electron density above and below the plane of the molecule in their conjugated p orbitals. Because these excess electrons are delocalized, however, aromatic compounds are poor bases, but they can still be used as nucleophiles. So in this image, I have several different representations of a benzene ring. I show the two resonance structures, or I show the two depictions of their resonance hybrids. So we can see that that electron cloud is delocalized, but that there is a lot of electron density in that cloud. In the images on the right, we can actually see the p orbitals, and we can see a depiction of the delocalized pi system, and you can see that those p orbitals extend above and below the plane of the benzene molecule. On that bottom right image, you can actually see where that charge is concentrated, so you can almost view the molecule as being able to attack from this negative area above the molecule or below the molecule. No matter which visual you prefer, the fact remains that the benzene ring and other aromatic compounds are nucleophilic, so they can attack regions that lack electron density. Now that we know why a benzene ring can be an attacking group, let's talk about electrophilic aromatic substitution reactions. On your screen, you can see a depiction of the general EAS reaction. We have a benzene ring, and we have some electrophile and some base, and you can see that electrophile gets added onto the ring, and we retain the aromaticity of the ring. Now, in particular, there are several different EAS reactions that you'll typically learn in organic chemistry, and I've shown what all of those look like on the left. Just like radical reaction mechanisms can be broken down into a series of steps, initiation, propagation, and termination, so can EAS reactions. Unlike those radical reactions, however, there are no consistently used names for the steps in an EAS reaction. So, like a great teacher, I decided to make up my own names. That way it can help you keep track of and make sense of how these reactions work. So I call the first step creation, and that's where we create the electrophile and the base. And I call the second step generalization. This is when we insert that electrophile and the base into that general EAS mechanism. Like I said, the 5 commonly taught EAS reactions are on the left, and the reactants above and below the reaction arrow are used in the creation step and will simultaneously make the electrophile and the base. The general EAS reaction, which is the image on the top, is used for every single one of those reactions shown on the left after the creation step makes the electrophile and the base. Because all of the EAS reactions use the general EAS mechanism, the general mechanism is the best place to start. We have our nucleophilic benzene ring, and we're going to draw an arrow from that to whatever electrophile was created in the creation step. When we draw the product of this, it looks exactly like what happens when you do an addition of an alkene. That is, we're going to create a new bond to that electrophile, and the double bond is going to be gone, which leaves behind a carbocation. Now the difference is, this carbocation is resonance stabilized. This resonance stabilized intermediate, as depicted here, is known as the sigma complex. And notice that we disrupt the aromaticity of benzene in this step. Because we're disrupting the aromaticity, this is actually the slow or the rate determining step of the EAS reaction. The next step of the mechanism is the fast step, as it restores the aromaticity of the ring. This step involves the base. So what we're going to do is where we added the electrophile, there's also a hydrogen in that position. And this step looks a lot like an E1 reaction. The lone pair on the base attacks the hydrogen, the carbon-hydrogen bond breaks, and we reform a double bond. This completes the substitution. As you can see in the final product, we've restored the aromaticity of the ring, and we have a new group added to where a hydrogen used to be. Now the question may come up that when you draw this mechanism, should you draw the entire sigma complex? And of course the answer to this is it depends. Some professors want you to draw the entire sigma complex and will penalize you for not doing so. Others simply want you to write something as simple as +2 resonance structures beneath your structure, just to acknowledge they exist. And another group won't care even if you pretend that there are no resonance structures, as long as you show the base properly removing the hydrogen to restore the aromaticity of the ring. So pay attention to what the expectations are in your class. The creation step, where we create the electrophile in the base, is different for all 5 of the EAS reactions. For nitration, we start with HNO3 and H2SO4. But there's a trick to making sure you understand this one better. And that is, instead of writing HNO3, we are going to write it as HONO2, or for fun, I call that HONO2. The important part about this is recognizing that the oxygen on this OH group on the end has 2 lone pairs. The next trick, and honestly you can do this anytime you see H2SO4, is to write H2SO4 as HOSO3H. And this more clearly shows that that hydrogen is acidic. So what we do next is really simple. We draw from our area of high electron density to our area of low electron density. In other words, from the oxygen to the hydrogen. And that, of course, breaks this oxygen-hydrogen bond on H2SO4. And what that does is it creates H2O, NO2, and it creates OSO3H negative. Now, there's a positive formal charge on this oxygen on H2O, NO2. So we have another step where this leaves as a leaving group, giving us water, NO2 plus, and OSO3H. And you can see that this is the electrophile with its positive charge on the nitrogen, and the OSO3H negative acts as our base. What we're going to do next is we're going to plug in the electrophile and the base into the generalization step so you can see what that looks like with an actual electrophile and base. As a reminder of what that generalization step looks like, I have the generic version of it shown at the top of this page. So what we're going to do now is we're going to plug in the actual electrophile generated in the creation step, which was NO2 with the positive charge on the nitrogen. And of course, the nucleophilic pi bonds are going to attack that nitrogen. That will give us this. Next, of course, we're going to take our base from that first step, which was OSO3H minus, and this is going to remove the hydrogen, regenerating our aromatic structure. And that's all you need to do. It is as simple as that. The creation step in sulfonation is a little strange, but once you see it in its entirety, it's actually pretty easy to understand. First, we need to look at SO3. And SO3 is a sulfur that is double bonded to 3 different oxygens. What's strange about this molecule is that sulfur is a period 3 element and oxygen is a period 2 element. That gives us these 3 double bonds that are a little different than what we're used to in organic chemistry. In fact, they act a lot more like single bonds that are polarized, with the oxygen having the excess electron density on it, and sulfur being more partially positive. However, rather than get into a long discussion on that, I prefer to view this under the lens that I view everything. Oxygen is more electronegative than sulfur. there are lone pairs on the oxygen, and we have pi bonds, which means that those oxygens are sufficiently nucleophilic and basic. So when we react them with H2SO4, or again, HOSO3H, it's really easy to just draw an arrow from one of these pi bonds to the hydrogen. That's going to give us a sulfur with a single bond OH and 2 double bond oxygens. And now we have a positive 1 charge on the sulfur. In addition, we created OSO3H negative. So once again, we've created our electrophile. That is SO3H with the positive sign on the sulfur, and the same base as we got in the nitration step, OSO3H. The generalization step for sulfonation should look almost identical to the generalization step for nitration, except that our electrophile is now SO3H instead of the NO2. So the nucleophilic benzene ring will attack the sulfur electrophile, and that will give us our sigma complex. Then our base attacks our hydrogen, recreating the aromatic ring. In our final product, you can see the SO3H has been added to the benzene ring. There is one more thing to note about sulfonation, and that is that it's the only EAS reaction that is easily reversible. In the absence of SO3, and with a low concentration of H2SO4, the SO3H that we added onto the benzene can function as a leaving group and then revert back to SO3, which will then escape the reaction chamber as a gas. This reversibility can be thoroughly explained with the Chatelier's principle. This feature of sulfonation can be used as a synthesis strategy to prevent the formation of para-substituted EAS products and only create orthoproducts, but that is a topic for another video. The creation step in halogenation is a little bit different, so in order to explore this more thoroughly, let's draw out Cl2, and we can either use FeCl3 with this or AlCl3. So I'm going to draw FeCl3. If we look at FeCl3, we should notice that it is electron deficient because it only has 3 bonds and therefore not a complete octet. In addition, we have 3 very electronegative chlorines bonded to a metal, which means that that metal is going to be positive as we would expect. Now Cl2, we know that each of these chlorines has 3 lone pairs on it. And these lone pairs, one of them we can use to attack this electron-deficient iron. It is a Lewis acid, so we can attack that. And what that's going to do is it is going to form a Lewis acid-base complex, ClClFeCl3. If we had used AlCl3, the same concept would apply. Now, this is interesting because this puts a negative formal charge on the iron and a positive formal charge on the chlorine. And to resolve this, we often get this step right here, which removes the electrons from the chlorine-chlorine bond and puts them all on one of the chlorines. This is a reversible process that gives us a Cl plus electrophile and a ClFeCl3 with a negative formal charge on the iron, and that is our base. In the generalization step for halogenation, we usually draw the entire complex on the line. So we'll draw ClClFeCl3 right here, and we'll show the nucleophilic benzene attacking the end chlorine and breaking this bond. Once we create the sigma complex, we can bring in the ClFeCl3 to act as the base to deprotonate the sigma complex and recreate the benzene ring. When drawing this step of the mechanism, notice that the arrow is drawn from the bond between the chlorine and the iron to the hydrogen. This breaks the chlorine-iron bond and gives us an HCl, and it regenerates our FeCl3 catalyst. In the creation step of Friedel-Crafts acylation, we're going to see something familiar, and that is we have another Lewis acid with AlCl3. So if we draw our starting material here and we react it with AlCl3, what's going to happen is the lone pairs on the chlorine will attack the electron-deficient aluminum, and that will give us another Lewis acid-base complex. Now, this ClAlCl3 is actually a good leaving group. So it is going to leave the acyl group, and that is going to give us this resonance-stabilized ion called the acylium ion, and our base, ClAlCl3. Once again, for our generalization step, we're simply going to plug in our electrophile, which in this case is our acylium ion, and of course we're going to attack that with the nucleophilic benzene ring. That is going to give us our sigma complex. Then, as usual, we're going to bring in our base that we created during the creation step, which in this case is the bond between the Cl in the Al and ClAlCl3, and we're going to use that to deprotonate the sigma complex and restore our aromaticity. Like we had in halogenation, we will have an HCl byproduct and we will regenerate our AlCl3 catalyst. We're saving our discussion of Friedel-Crafts alkylation for last, and that's because there are so many variations to Friedel-Crafts alkylation, and that's what makes it the most complicated of the EAS reactions. What we have to consider is our starting material. We have some RCl group and AlCl3. But the identity of the R group matters. So let's take a look at what happens when we have a methyl chloride or an ethyl chloride and react that with AlCl3. The first step should be very familiar because the lone pairs on the chlorine are going to attack the AlCl3 and form a Lewis acid-base complex. Now, normally, we say that ClAlCl3 is a good leaving group. However, if it were to leave in this case, it is going to cause a problem. And that problem is we would have a first-degree carbocation, which can't exist. So in other words, if we have a methyl or an ethyl chloride, the Lewis acid-base complex itself is both the electrophile and the base. When we react any other primary alkyl chloride other than an ethyl chloride with AlCl3 in an EAS reaction, we get a very interesting result. The first step, of course, looks identical, where the lone pairs on the chlorine attack the AlCl3, giving us a Lewis acid-base complex. What happens next is very strange. Again, the ClAlCl3 is a good leaving group, and we'd normally say that it can't leave because that would create a primary carbocation, which can't exist. But when it comes to these reactions, we can actually do a 1,2 methyl shift or a 1,2 hydride shift without having ever generated the carbocation in the first place. So what we're going to get is we're going to do a 1,2 methyl shift in this case, and the leaving group is going to leave at the same time. And this is one of the only areas in organic chemistry where this happens, where we get the 1,2 hydride or methyl shift or the carbocation rearrangement without ever initially generating a carbocation. This rearrangement is going to give us a tertiary carbocation, which acts as our electrophile in the generalization step, and our base, ClAlCl3, which we've seen several times now. The takeaway from this is that if your R group is longer than an ethyl group, you will always get this strange carbocation rearrangement, and will get a different electrophile than you would expect in your generalization step in the EAS reaction. Fortunately, for secondary and tertiary alkyl chlorides in this reaction, nothing that you haven't seen before happens. So what we're going to do is we're going to use the lone pairs of the chlorine to attack the aluminum and form our Lewis acid-base complex, just like we did in all of the other steps. This is a good leaving group, so it is going to leave, and that is going to give us a secondary carbocation. Now, in this case, we do still need to look out for carbocation rearrangements, but we should be doing that anytime we generate a carbocation anyway, so this is nothing new. In the previous reaction, it was new because we never actually generated the carbocation. So here we can do a 1,2 hydride shift and go from a secondary carbocation to a tertiary carbocation, and we're going to use that in our EAS generalization step. Of course, we do have that ClAlCl3 that we can use as the base, just like we had it in all of those other reactions. Now, the first rule that I give my clients when I talk about Friedel-Crafts alkylations is that when you think you're done talking about Friedel-Crafts alkylations, you're wrong, because there's more to talk about with Friedel-Crafts alkylations. And in this case, we have two other ways to do Friedel-Crafts alkylations in the creation step. So what I say is, anytime you can generate a carbocation and a base in the same step, you can use that in a Friedel-Crafts alkylation. Now, there are plenty of other things to learn about Friedel-Crafts alkylations that are beyond the scope of this video, but that are covered in other videos. So what we're going to do here is analyze two more Friedel-Crafts alkylations. The first one involves an alkene and H2SO4. If you remember, alkenes have a nucleophilic and basic pi bond, and H2SO4 we can rewrite as HOSO3H. The nucleophilic and basic pi bond is simply going to attack this partially positive hydrogen, and that's going to break our hydrogen-oxygen bond. And if you remember from the reactions of alkenes, that is going to give us our secondary carbocation here, which is going to be the electrophile in the generalization step, and we're going to get our OSO3H base. Of course, anytime we generate a carbocation, we should look out for carbocation rearrangements. This one doesn't have one to worry about. The next Friedel-Crafts alkylation involves an alcohol with H2SO4. So in this case, we have our alcohol, and if you remember reactions with alcohols, oxygen is not usually a good leaving group. But if we protonate it and turn it into OH2, which we can do because there are lone pairs on the oxygen and they can attack this acidic H2SO4, we can actually turn this into an OH2 with a formal charge on the oxygen, and that is a good leaving group. So now we have that molecule with OSO3H, and the OH2 plus is going to leave, which of course is going to give us H2O, an electrophile, which is a secondary carbocation in this case, and our base, OSO3H negative. And once again, we can plug in that electrophile and that base into the generalization step of our Friedel-Crafts alkylation. Because there are three different electrophile and base combinations that we could have gotten from the various Friedel-Crafts alkylation pathways, we have three different things that we can plug into the generalization step. In the first example, we created a complex that was both the electrophile and the base. So the nucleophilic benzene ring attacks in a reaction that looks awfully similar to an SN2 reaction, where we attack the electrophilic carbon and we kick off a leaving group. This generates our sigma complex and also gives us our base, our ClAlCl3, which of course we can use to protonate the chlorine and regenerate our aromatic ring. For every pathway that wasn't a methyl chloride or an ethyl chloride, we generated either a secondary or tertiary carbocation. So the nucleophilic benzene ring is going to attack the carbocation in both of these cases. And of course, that's going to generate our sigma complex for both of them. In these two cases, however, it was the base that was different. In the one, we had a ClAlCl3 as the base, and in the second one, we had an OSO3H as the base. Of course, we've seen both of these bases before, so we are going to deprotonate and regenerate our aromatic ring in both these cases. And there you have it, the final two generalization steps for Friedel-Crafts alkylation. For most EAS questions you're going to see in an organic chemistry class, you will simply be asked to predict the product of an EAS reaction. However, asking for an entire mechanism for an EAS reaction is a favorite type of question for a lot of professors, which is why I wanted to review each of these in such detail. If you got something out of this lecture, Please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.